Welcome to the fourth lesson of the Unbalanced Force unit. Today we are going to be putting together some of your favorite things. We're going to be putting together kinematics, which is about motion, and Newton's second law. In fact, maybe I could even put this better. We're going to put together our constant acceleration model, and so when you're talking about Newton's law, we're really talking about our unbalanced forces model. We're going to put those two together. So for most of these questions here, we're going to follow these steps. We're going to use a force diagram. We will use a force diagram to find the net, or the unbalanced amount of force, and we're going to list all our unknowns. So in the unbalanced force model, the three things that we're looking for is acceleration, mass, and net force, or Fnet as we often write it. And here's the mathematical model of how those three fit together. When we're talking about kinematics and we're talking about constant acceleration, we got acceleration, initial velocity, final velocity, change in time, and displacement. And so we can put those together. Remember, we had our big five, and we can organize those according to which one is not in there. So in the first one we don't have a VF, a final velocity. The second one we don't have an initial velocity. Third one we don't have an acceleration. Here we don't have a displacement. And the last one we do not have time, change in time. So these are, this list here, if you don't have it already, should be in your notes somewhere so you can access it during a test. And you'll notice that what ties these two together is acceleration. So sometimes you're going to have enough information. You might be given mass and net force, and you can use that to find acceleration, and then you'll import that into the kinematic side, the motion side, or sometimes it's the other way around. So let's try this together. We're going to try question number 1, and it says a student pushes a 2 kilogram frictionless lab cart with a force of 10 newtons. Okay, so I don't know, sometimes a picture is kind of nice to see what's going on. So maybe here's this lab cart, and the person's pushing on it. So I'm going to draw this force to the right over there. So if we're going to make a quantitative force diagram, that means we're going to put some numbers into it. So first of all, how is this person pushing it? Well, if they're kind of using their finger to push on it, you could call it a normal force. Lots of times when we're just talking about a force that someone's applying to an object, but we're not really too worried about what type of force it is, sometimes we just say applied force. So you can see both of those. So that would be this normal force or applied force to the right, and that one they tell us, is that the one we say? Yeah, is 10 newtons. Now if the object has a mass of 2 kilograms, then we can say that there is a force of gravity downwards of 20 newtons, and the only way that this object is going to be accelerating is to the right. So we know that the vertical forces are going to be balanced. It's not going to be accelerating upwards or downwards. So even though I'm getting a little into the text here, I'm going to say that this normal force is equal to 20 newtons. Okay, so we've made a quantitative force diagram, check. Now it says write a net force equation for the axis along which the forces are not balanced. Well, I think the other thing I'm also going to do is just talk about how I'm going to refer to directions. So I'm going to be talking about this horizontal direction, because that's the direction that acceleration is going to take place, and I'm going to say that to the right is positive. And so when I make my Fnet statement here, so I'll say Fnet is going to be equal to, well, there is only one to the right, so it's going to be the same thing as this applied force to the right. Okay, so that sounds great. Now over here I'm going to talk about our two types of equations. We got our Fnet, our mass, and our acceleration. And this is part of our unbalanced force. And we also have here our constant acceleration. So those are sort of our two models here. Maybe if just for the first time I'll write it out. Unbalanced forces. And here is our constant acceleration. If I was just going at a constant velocity, we wouldn't have to bring out the big 5. Okay, so in our constant acceleration we have VI equals VF equals acceleration equals displacement equals, and the change in time equals. So we got all those different things. All right, so let's try to fill in what we know. Maybe I'll go green for that. Okay, so we know that this force to the right is actually 10 newtons. So we know that this is 10 newtons here, so this net force is 10 newtons. We know that the mass is 2 kilograms. Oh, so right away we can figure out what the acceleration is. Well, acceleration is equal to Fnet over m. So it's going to be 10 divided by 2 is 5. So here our answer is 5 meters per second squared. Now, it's always a good idea just to think about whether it's in a positive direction or a negative direction. Quite clearly, this is in the positive direction because I'm looking here. This is in the positive direction. Okay, so I'm going to import that over to the right-hand side. I'm going to say plus 5 meters per second squared. And what are the other things we know? It pushes the cart with a force. If it pushes for 2 seconds, so clearly this is 2 seconds here, how far will it move? How far is a question of displacement? So that's the question mark. And it doesn't say explicitly, but I think we can make a presumption here that it starts from rest. And so we're not going to be using our VF. So which one does not use VF? It looks like equation number 1. So we bring out equation number 1. And equation number 1 says the displacement is equal to VI times the time plus 1/2 a delta t squared. Since the initial velocity is 0, this whole term here gets cancelled out into 0. I kind of like putting an arrow in there and saying 0. So it's going to be equal to 1/2 multiplied by the acceleration, which is 5, multiplied by the time squared. Don't forget that squared. I don't know why, there's a bit of a habit that people sort of miss that one. Which is equal to, it's easy to multiply the 1/2 times the 4 first to get 2, and then 2 times 5 is 10. So the answer is 10, and it's going to be 10 meters. So if she pushes for 2 seconds, how far will it move? Our answer is 10 meters. So we got the first question. And now the second question says, find the cart's final velocity, VF equals question mark. So you got a lot of choices about what you're going to use for this find the cart's final velocity, which is one of the easiest ones. Probably equation number 4 here. So it's already set up for the final velocity. So we'll say VF equals VI plus a delta t. So, and this kind of makes sense, isn't it? The final velocity is going to be equal to how quickly it was moving to begin with, a plus, if the velocity is changing by 5 meters per second every second, and this happens for 2 seconds, it's going to be 5 times 2. It's going to be 10 meters per second. So that is the answer to our second one. Okay, so that's the first question. I would like you to try the your turn, and I think it would be a good idea to sort of use this same structure that I used. Draw a force diagram and make it as quantitative as you can. Include which direction we're talking about the motion, and then you can do your unbalanced force model and the constant acceleration model. Okay, so I'd like you to hit pause and give this one a shot now. Thanks. Alright, so here's my answer. I drew my diagram. It didn't have the name of some force which is causing it to accelerate, so I just called that FA, but it didn't really matter. It's nice to have a habit of labeling all your forces, so I said here there's an Fnet, is the same thing as whatever that force was that was causing it to accelerate. In this case, we actually used our kinematics, our motion variables, to try to figure out what acceleration was, and we didn't use the final velocity, so I chose equation number 1. I ended up getting 110 over 9, so I got 12.2 repeating meters per second squared. Here's a pro tip: leave that in your calculator, and then just keep carry it over for your next calculations instead of rounding. So I'll just write here, don't round yet. Just keep all that. And now, so this went into here, 12.2 repeating. I can put that in there. And so that got copied over to our other side. And now we got our Fnet equals ma lined up. Multiply that out and I get 6,111 newtons. Excellent. Okay, let's take a look at number 2 here. A 50 kilogram diver is traveling at 15 meters per second when she enters the water. Okay, so here, let's just think about what's going on here. So here's this person. maybe I'll do a motion map, and they're going downwards, right? So here's they're going downwards, and then all of a sudden they hit the water. So let's say, there's the water. So they hit the water, and she comes to a stop in 4 meters. So I don't know exactly what my scale looks like, but clearly they slow down. So if I was to say to begin with here, that this one here, they're going some velocity. In that case, it would be 15 meters per second. And then she's slowing down and getting closer and closer to 0 until she stops. And so this distance that they travel here, this distance here, from here to here, well, first of all, that's the distance that they travel, but which way is positive and which way is negative? I'm going to actually say that for my scale here, that this way is positive. So in fact, this person is, the velocity is at down or negative. Because usually we like to say up is positive, and a diver going into the water is going downwards. And if you look at it, because she's slowing down, if you're going downwards, but you're slowing down, that means your acceleration is up, or in this case, positive. So the velocity is negative and the acceleration. So velocity is going to be negative and the acceleration is going to be positive. Alright, in the meantime, let's draw a force diagram. And just remember, the part that we're interested in is after this diver enters the water. So maybe I'll just remove these first dots because we're not interested in when she's not in the water yet. So she's in the water. Clearly there's going to be a force of gravity downwards. That force of gravity will be 50 times 10, so that will be 500 newtons. And now there's the force of the water, and I think we'll just call this F water. And which way will that be? Well, if the acceleration is up, then the F net is also going to be up. Okay? Why? Because, well, first of all, it's going to be up not just the same as the length of the force of gravity, but has to be even greater than that, because the net force, the sum of them added together, or the amount that they're unbalanced, has to be up. So I'm going to put this up here as F water. Now we'll make our F net statement. F net is going to be equal to the F water, which is up, so it's positive. Now the force of gravity is downwards, it's negative, so I'm going to say minus the force of gravity. Okay, so notice it's a little bit different than our other ones. In our other ones, even when there were vertical forces, we said, yeah, we're not worried about them because they're canceling each other out. So we wrote our F net on the horizontal axis. In this case, it's unbalanced in the vertical direction. So our F net is really in that vertical direction. So this is the way it's going to look. Okay, so now over here we can draw our unbalanced forces thing. So it's going to be F net equals mass equals acceleration equals. In the meantime, we'll do our constant acceleration. We'll write out our big 5 here. VI, VF, maybe acceleration now, displacement, and time. And what are the things we know here? Well, they're traveling at 15 meters per second, so it starts at 15 meters per second. She comes to a stop, so this is 0 meters per second after 4 meters. Now we've got to be careful. In fact, you know what? I don't want to have delta x because they're moving. Oops, this diver, she's moving vertically, so I'm going to say delta y in this case. It's not about right because this x we use for this kind of motion, y we use for that kind of motion. And in the meanwhile, which direction is she moving? Well, she's starting from here and she's ending this way, so my delta y is actually downwards, isn't it? So I'm going to say if she comes to a stop 4 meters below the surface, this will be minus 4 meters. Okay, so a bit of a important thing to look for. And what do we know? We want to find out the acceleration because we want to import it to the other side. So we're not going to be using time. So which equation does not use time? I've got to go way up over here. See, the one that does not use time is number 5. So that VF squared equals VI squared 1. Okay, so we'll go over here. I'll make some space for myself here. So equation number 5, Vf squared equals Vi squared plus 2a. Now normally we'd say delta x, but now we're doing delta y because it's vertical motion, but it works exactly the same way. So 0 squared is 0 equals 15 squared plus 2 times a times negative 4. So 15 squared is 225. Now the 2 and the minus 4 is minus 8a. So I can add 8a to both sides. And when I divide both sides by 8, 225 divided by 8 I think is 28 and an eighth, so 28.125. So I got that, and again I'm just going to remind myself I'm not going to round it yet, so maybe I'll use red just to make it really prominent. Here's my 28.125, and then that goes also over there. I'll do this last part in red. So I'm going to say now I've got the acceleration figured out, and I know the mass, don't I? It's 50 kilograms. So here I'm going to say Fnet is equal to mass times acceleration. So it's going to be 50 multiplied by this 28.125, which is 1,906. No, 1406, pardon me. 1406 newtons. If you get your calculator out, that's what you get. And you might think we're done, except for we don't want to know the net force. We want to know the force of the water. So back over here, we're looking at this Fnet, and I'll say this Fnet was 1406. So in other words, the net force must be upwards, right? And it's 1406. In other words, the force of the water up is 1406 greater than the 500 downwards. So if I plug this in here, I'm going to get force of the water minus 500. Now if I add 500 to both sides, now I get 1906 is equal to the force of the water. And there we go. There is our final answer. Excellent. Okay, so for this last one, it's I wrote a little pretty picture of a bottle of water, and it's given a push to cause it to start moving. I want you to give this one a shot on your own, and then when you're done, take a look. So I got things set up here. I figured if it's moving to the right, then the friction has to be to the left. So I still said rightward is positive. So just down here I was thinking, okay, that means the velocity is positive and the acceleration is going to be negative. It's slowing down. The friction force is in the negative direction, so I said Fnet is equal to negative the friction force, so the Fnet is negative 5. So over here when I do my calculations here, I can figure out that acceleration is going to be equal to the Fnet over m, and that will end up being negative 3.3 repeating, and that also goes over here. And after I plug in my numbers, I think I get a 2.0, a 0, a question mark here. I don't use time, so I'm going to use equation number 5. And when I plug it into equation number 5, the math gets a little tricky here. I put in the 3.3 repeating, and when I follow it through, I do get exactly 0.6 meters, which would be the same thing as 60 centimeters. I hope you did well on that. And so you can go on and check out the worksheet, and I will see you in class.